In this example, we will once again evaluate the work in a polytropic process. The goal here is to pull everything together that we've done up to this point. For this problem, we have some measured data, and we don't know the polytropic constant N. Let's return to our piston cylinder from an internal combustion engine. We will evaluate the work done during the power stroke. Just after combustion, the pressure in the cylinder is 1852.81 kilopascals. The temperature is 1086.3 Kelvin, and the volume is 0.2 liters. At the end of the power stroke, the volume is 1 liter. During the expansion process, the pressure in the cylinder was measured, summarized in the table. The task is to estimate the work done, first using the measured data. Second, we will find a polytropic constant N that fits the data and compute the work using the integral of P dV. From our integral work equation, we can see that the work done is the area under a curve on a PV diagram. We can compute this area using the trapezoid rule. Remember that the area of a trapezoid is 1/2 times base 1 plus base 2 times the height. From our graph, the area is 1/2 times P1 plus P2 times V2 minus V1, where 1 and 2 are at the start and end states for this portion of the overall process. We can compute the work by performing a trapezoidal integration over each region of the measured data. Note that the units must be adjusted. When we plug it in, we see that work is 1/2 P1 measured in kilopascals plus P2 measured in kilopascals times V2 measured in liters minus V1 measured in liters. This will give us an answer in kPa times liters, which we can convert into kilojoules. First, we know that 1 kPa is 1,000 pascals. We know that a pascal is a Newton per meter squared. A liter is 10 to the minus 3 meters cubed. And so this tells us that 1 kPa liter is equal to 1 Newton meter, or 1 joule. We know that 1 Newton meter is a joule, and that 1,000 newtons per kilonewton can convert this to kilojoules. 1 kilojoule is 1 kilonewton meter. And so we're left with 1 kPa liter is equal to 1 over 1,000 kilojoules. Now apply the trapezoidal integration to each portion of the measured data and use the proper unit conversion. And so what we're doing is we're integrating over each of these areas using a trapezoid rule. Once we have the area for each region, we add them all together and we get the work for the entire process. The result is 0.54 kilojoules. Remember from our previous examples that the work for the isothermal and adiabatic processes form the upper and lower limits of the work that can be extracted. The isothermal work was equal to 0.597 kilojoules, and the adiabatic work was equal to 0.44 kilojoules. The true process is somewhere between adiabatic and isothermal. Some heat transfer is occurring, though not enough to maintain a constant temperature. Now let's try and find a value for the polytropic constant N that matches the data. Once we have a value for N, we can perform the integral directly to compute the work. Let's start with an isobaric or constant pressure process. Remember that for an isobaric process, N takes the value of 0. So we have PV to the 0 equals a constant. In other words, pressure is a constant. And so we plot this pressure for each volume measurement. and we see that the predicted values do not match the measured data very well. Next, let's try an isothermal, or constant temperature process. Remember that for an isothermal process, n takes a value of 1, and so we're left with PV equals a constant. We can evaluate this relation at the initial state to determine the value of our constant C. P1V1 equals C, equals 1852.18 kPa times 0.2 liters, which is equal to 370.436 kPa liters. Using this value of C, we can compute the pressure at each measured volume by solving for P, where P is just C divided by V, or 370.436 kPa liters divided by our volume, which is measured in liters, and so the liters cancel and we're left with a value of pressure. We plot the computed pressure for each volume measurement and see that the computed pressures match the recorded data better. In general, this value of n overestimates the pressure value. Next, let's try an adiabatic, or no heat transfer process. Remember that for an adiabatic process, n takes the value of the ratio of specific heats. This value is represented by a K and depends on the substance as well as the state. Let's assume the value is air at standard atmospheric conditions. At these conditions, the value for K for air is 1.4. Once again, we can compute our constant C by evaluating at state 1. Note that the value as well as the units will be different than for the isothermal gas. Again, we substitute the values for the initial state to compute C, 1852.18 kPa, times V1, which is 0.2 liters, raised to the 1.4, which is equal to 194.592 kPa liters to the 1.4. Note the strange units on C. This is okay because they will cancel when we evaluate the pressure. Many constants that we will encounter will have strange units. We compute the pressure for each measured volume in the same way, using the polytropic relation solved for pressure. And so we have that pressure is equal to our constant divided by V to the K, which is equal to 194.52 kPa liters to the 1.4 divided by the volume to the 1.4. We plot the computed values and see that these pressures slightly underestimate the measured data. Now that we have bracketed our data by a slight overestimating and underestimating values of n, we know that the true value of n is between 1 and 1.4. This means that the true process was somewhere between an isothermal and an adiabatic process. Remember that an isothermal process has just enough heat transfer to maintain a constant temperature, while an adiabatic process has no heat transfer. The true process must have some heat transfer, but not enough to maintain a constant temperature. Let's try a value for n between 1 and 1.4. After several guesses, we see that a value of 1.2 fits the data well. Once again, we must evaluate the constant at state 1. P1V1 to the n is equal to a constant. And so we solve. Our constant is 1852.18 kPa times V1, which is 0.2 liters, raised to the n, which is 1.2. And so our constant is equal to 268.484 kPa liters to the 1.2. Note that the values for C and the units are different again. Now we compute the pressure for each measured volume using the polytropic relationship. PV to the n is equal to a constant. And so we solve for pressure and see that pressure is equal to the constant divided by V to the n, which is 1.2. We sub in our value of C, and we compute for each measured value. Adding these values to the plot, we see that the estimate matches the measured data well. In fact, it covers over the other line. And so we know that our n is 1.2. Now that we have correctly identified our polytropic constant, n equals 1.2, we can integrate to compute the work done in this expansion process. We start with the integral definition of work. Work is equal to the integral from v1 to v2 of p dv. We solve the polytropic relation for pressure and substitute. PV to the 1.2 is equal to a constant, and so pressure is equal to the constant divided by V to the 1.2. We sub this into our work integral and perform the integration, and we see that the work is equal to the constant times V to the 1 minus 1.2 divided by 1 minus 1.2, evaluated at V1 and V2. Remember that pressure is equal to the constant divided by V, and so we can sub in for our constant PV to the 1.2. PV to the 1.2 times V to the 1 minus 1.2, all divided by 1 minus 1.2, evaluated at V1 and V2. You see there that the exponents add, and we're left with PV divided by 1 minus 1.2, which is minus 0.2, evaluated at volume 1 and volume 2, which finally becomes P2V2 minus P1V1, all divided by minus 0.2. Now we sub our values in for the beginning and end states of our process. First we need to find a value for P2. We can compute it using the polytropic relation. P2V2 to the 1.2 equals a constant. Solving for P2, we see that P2 is equal to the constant divided by V2 to the 1.2. We substitute in our values, 268.484 kPa liters to the 1.2, that's our constant, divided by volume 2, which is the volume at the end state, which was 1 liter, raised to the 1.2. And it tells us that our pressure is 264.484 kilopascals. We substitute that into our work calculation. We find that the work is equal to 264.484 kilopascals times volume 2, which is 1 liter, minus P1, which is 1852.81 kilopascals, times V1, which was 0.2 liters, all divided by minus 0.2. The work is equal to 530.39 kPa liters, which we can convert into joules by recognizing that 1 joule is equal to 1 kPa liter, which we found above, and 1,000 joules is 1 kilojoule. And so we have that our work is 0.53 kilojoules. We see that this value matches the value that we obtained by integrating the measured data using the trapezoid rule. But note there's a small difference. The difference is due to the fact that the numerical integration we performed used a trapezoid rule, which does not give an exact result. Because the value of n we chose matches the data so well, we can assume that the integrated value is more accurate.